The first part of Chapter 6 was all about learning about symmetry and understanding symmetry elements, symmetry operations, and symmetry groups. What we're doing now is to use those concepts to build up the molecular orbitals of a molecule from the atomic orbitals of the atoms that make up that molecule. So for instance, you're fairly familiar, I think, with the molecular orbitals that are the usual ones that we use for a diatomic, such as nitrogen. So here I've shown only the valence electrons in nitrogen. There is also a 1s, sigma s bonding and sigma s antibonding that belong to the 1s core electrons in nitrogen, but I haven't shown those here. So we think about the atomic orbitals on each nitrogen combining to form these molecular orbitals that we're sort of familiar with. A sigma bonding orbital where there's electron density between the two nuclei, a sigma anti-bonding orbital where there's a node between the two nuclei, and then we have some pi orbitals that are formed from overlap of p orbitals in the nitrogen atoms, and we have both pi bonding and pi anti-bonding. And then we also have this sigma orbital that is formed from combining p orbitals that are oriented along the bond axis in the nitrogens. So we have a bonding sigma orbital from the combining the p orbitals, and an anti-bonding with a node between the two atoms for the combining the p orbitals that are aligned along the molecular axis. So that's our normal description from general chemistry of these molecular orbitals. What we need to keep in mind is that molecular orbitals are actually an overlap of all the possible electrons within nitrogen. And so we've used sort of a local bond model where we've just thought about the two s orbitals combining, but in reality, this sigma bond right here is a combination of the s orbitals and the p orbitals that are aligned along the axis, because both of those orbitals have the right symmetry to combine and form electron density between the two nuclei. And so in reality, these, if we really did a true molecular orbital calculation, we would be using the entire basis set, all atomic orbitals on both nitrogens, and combining them together to form the different energy states of the nitrogen molecule. And in fact, as your book points out, there's not one set of molecular orbitals that is the true set of molecular orbitals. Each set of molecular orbitals that we come up with is simply a representation of the bonding within nitrogen. So we have chosen to construct our molecular orbitals in a particular way here, and that's not the only way that we could do it. So remember that these molecular orbitals are basically pictures of the electrons as a wave, and the way in which all of those electrons that are part of this nitrogen molecule are overlapping. All of those waves are overlapping and forming interference patterns, if you will, to form new wave patterns, new interference wave patterns. And that's what these molecular orbitals are. But in order to preserve some understanding of where the electrons are coming from to form these different molecular orbitals, what we do is we form symmetry molecular orbitals. So we look at the molecular orbitals that have particular symmetry properties within the point group of the molecule. So for diatomics, all diatomics are either represented by d infinity h or c infinity v, depending on whether they are homonuclear or heteronuclear. So all of those are described by sigma and pi symmetry elements, which are parts of the c infinity v and d infinity h point group. So once we decide on our representation of our molecular orbitals, we can assign those molecular orbitals to particular symmetry elements or symmetry representations within the group by thinking about how this particular shape transforms using the symmetry operations in the group. So we can define a reducible representation for each one of these possible shapes, and then we can reduce it to get the irreducible representation for each of these shapes, each of these molecular orbitals that we have used to describe our molecule. And in this case, we have sigma symmetry for these guys, we have pi symmetry for these guys, and sigma symmetry for these guys. Now, the way that we would normally do this in our symmetry representation is that rather than using a star for the anti-bonding orbitals, the bonding orbitals are going to be symmetric with respect to the inversion symmetry, and so they're going to be sigma g, and the anti-bonding orbitals are going to be anti-symmetric with respect to inversion, and so they're going to have a sigma u. So rather than using the star, which is your way in which you're used to thinking about these molecular orbitals, we're going to use the labels gerada and ungerada to describe the orbitals in terms of their representation based on the inversion. So notice that the sigma antibonding orbital has both a negative and a positive lobe. We've just used different colors to represent that. And so if I do the inversion operation where I just take everything across the center to the other side, everything changes sign, and so it's a -1 in terms of inversion, so it's anti-symmetric with respect to inversion, and so I have a sub u for those anti-bonding orbitals. Notice that in the case of the pi orbitals, the bonding pi orbitals are anti-symmetric with respect to inversion. If I go across the center, I change the sign. And so for the bonding pi orbitals, we have pi ungerada, whereas for the anti-bonding pi orbitals, if I invert, go across the center, the sign does not change, so it's symmetric with respect to inversion. And so for the pi anti-bonding, it is pi gerada. And therefore, you cannot just assume that if your orbital has a ungerada, it is anti-bonding, and if it has a gerada, it is bonding, because the pi orbitals are opposite of that. It's important to note that we have described these molecular orbitals as though they belong to particular electrons. And so we've assigned 2 electrons to this molecular orbital and 2 electrons to this molecular orbital, and so forth and so on. And so these molecular orbitals are somewhat analogous to the Hartree-Fock self-consistent field atomic orbitals, in which we divided up the overall wave function for the entire many electron atom into individual wave functions for each of the electrons in that atom. The overall symmetry, or the overall molecular orbital for the nitrogen molecule, would be a direct product of all of these atomic orbitals. And that direct product could be reduced into an irreducible representation to give an overall molecular term for the ground state, which is described by these particular 1 electron molecular orbitals combined together to form this lowest energy state. Notice that the lowest energy would be the energy, the sum of the energy of all the electrons in this nitrogen molecule, similar to the way that we get the 0 order energy for the Hartree-Fock self-consistent field many electron atoms. So to get the overall term symbol for the overall molecular configuration or electronic configuration of N2, we have to take the direct product of every molecular orbital that we have assigned electrons to. So we have 2 electrons in the core sigma bonding orbital that's formed primarily from the core 1s electrons and the anti-bonding orbital that's formed from those. So that takes care of the 4 core electrons. And then we have the 2s electrons primarily forming these sigma G and sigma U. And then we have our 4 electrons that are in the pi orbitals, and then our final sigma G bonding orbitals from the 2p orbitals that are along the bond axis. And so we need to take a direct product of all of these, and we can see that the sigma G is completely symmetric. The sigma U is symmetric with respect to the principal rotation axis and the vertical planes, and anti-symmetric with respect to inversion, the improper rotation, and the C2 rotation axes. So if we take a direct product of a sigma U and a sigma U, all of these negative signs will become positive, and so that direct product will be completely symmetric and will equal the sigma G. Sigma G times sigma G just gives us sigma G. So all of these, as long as we have 2 sigma U's, all of these sigmas are just going to give us sigma G. So we take sigma G, and then we take the direct product of pi U, pi U, pi U, and we can see that the pi ungerada is going to, everything's going to get multiplied by 2, and these rotations, because it depends on the angle through which we rotate it, is going to be 2 times the cosine of phi. These pi orbitals have 180 degree symmetry, and so we're just going to use cosine of 180, which is just equal to 1. And so if we take pi times pi times pi times pi, we get 2 times 2 is 4, times 2 is 8, times 2 is 16. So we get 16, 16, 0, and then 16 again because we have an even number of minuses, and then 16 again, and then 0. And so our reducible representation for this is going to have characters of 16, 16, 0, 16, 16, and 0. If we decompose this representation, we can see that there are an infinite number of characters in the group. So we have 1 over infinity times an infinite number of sigma plus G plus an infinite number of sigma minus G plus an infinite number of pi G plus an infinite number of pi U plus and so on. So the overall symmetry of this ground state consists of sigma plus G terms, sigma minus G term, a pi G term, a pi U term, plus some higher order terms.